So momentum's conserved, but what about the energy? If we calculate the total kinetic energy before and after the collision, would you expect it to be the same? So that's my question. We've got two skaters beforehand, both have got individual kinetic energies. If we work out the kinetic energy of the first person, add it to the kinetic energy of the second person, will that be equal to the combined kinetic energy? Will that be equal to their kinetic energy after they've joined together? Well, shall we work that out, because we've got all the information? So, kinetic energy is a half mv squared. So the total kinetic energy before, EK before, half m1u1 squared plus half m2u2 squared, substituting in, gives us 2,680 joules. The total kinetic energy afterwards, we need to use the combined mass times the final speed squared. Substituting in gives us 2,404 joules. It's clearly got lower, hasn't it? There is a loss of kinetic energy, a difference of 276 joules. Was that what you expected? It sort of might not have been. I wouldn't have thought. So, if I worked out the percentage change, the difference divided by the initial is 10%. It's 10% different. So we call it an inelastic collision because the total kinetic energy is not conserved. Remembering the law of conservation of energy though, energy can't be created or destroyed, only changed from one form to another. The energy must go somewhere. Usually, it's a vibrational energy of the particles involved, or of the air around, by which we mean as heat or sound, as in it's usually heat or sound are our normal wasted products. If there's any place where there's not something efficient, or completely efficient, it's heat and sound that normally take it away. And the same here. The bodies may also be deformed. We normally assume in momentum experiments that the two objects don't change their shape. But if we're looking at something like a bouncy ball, does it change its shape? Because that makes a difference to what's going on. It might have lost energy because of the bonding energy of the two objects. If they stick together, there might be some energy in forming that bond, for instance, especially if it's a chemical reaction. Because remember, momentum conservation applies from atomic scales right up to galactic. So it could be a chemical reaction between the two particles. It could be a gravitational interaction between the two galaxies. If we looked at nuclear collisions, for instance, inelastic scattering there might cause the nucleus to become excited, or even to break up. It might cause decay of the nucleus. That is one of the things that happens in a nuclear reactor, as in it's uranium nuclei get bombarded with neutrons. The collision between the neutron and the uranium nucleus causes the uranium nucleus to break apart, releasing energy. In other places, it might cause the nucleus to get excited and then de-excite, emitting gamma radiation. Incidentally, this deep inelastic scattering that I was just describing, Stanford Linear Accelerator discovered the internal structure of baryons and mesons like that. So if you think way back when to when we did about quarks, that is how quarks were discovered. We fired in protons and electrons and things at the centre of an atom and found point-like objects inside based on conservation of momentum, amongst other things. All collisions are technically inelastic. However, we normally consider an idealised situation called elastic collisions. In a perfectly elastic collision, kinetic energy is not lost to other forms, such as heat, noise or potential energy. The total kinetic energy will remain the same then. The kinetic energy before will equal the energy afterwards in an elastic collision. In ideal gases, we would normally model collisions as elastic. It's a very good approximation, that's why. Rutherford scattering, for instance, is elastic, where we fire the alpha particles into the gold foil nucleuses. it's a good approximation to say that that is elastic scattering, because there's no bonding or anything or energy lost when those alpha particles go in. Thinking about the energy changes in an elastic collision, the object's kinetic energy as it goes in, if we consider the Rutherford scattering example, the alpha particles got a certain amount of kinetic energy when it goes in, based on what radioactive decay it was. More about that next year. That kinetic energy, as it gets closer to the nucleus and feels more of an electrostatic repulsive force, will get changed into potential energy, until at some point the repulsive force becomes that great it repels it in the other direction. So then the potential energy it has from being close to positive charges close together gets changed back into kinetic energy. So at every point, yeah, the energy is changing from one form to another, but we're only interested in initial is equal to final at the start and at the very end. So in summary then, in all collisions, linear momentum is conserved. Why do I keep emphasising linear? Because there is such a thing as angular momentum. It is not on our spec, it is the engineering optional module, and we don't do that one. So it is A-level standard to know about angular momentum, but we don't cover it, and you don't need to know about it, just, in case it comes up. So we're only on about linear momentum, things moving in straight lines, not angular momentum, things moving in circles. But either way, linear and angular momentum are both conserved. In some collisions, some kinetic energy is converted to heat and sound or other types of energy, and those are called inelastic collisions. If only a tiny proportion of the kinetic energy is converted, then we say that it's elastic. We're basically saying if practically zero, it's all about the practically there. It's never zero, because that would be an ideal situation, but it's practically zero. If only a tiny proportion of that, then it's elastic. If the kinetic energy loss is large, then it's an inelastic collision. The extreme example of an inelastic one is the example we did where the two objects stick together, but then they also remain stationary afterwards. So they've lost all of their energy. They started off with some energy, they were both moving, and then afterwards they've got no kinetic energy. A perfectly elastic collision conserves both linear momentum and kinetic energy, and it's an ideal situation. It doesn't really happen, but normally it's a good approximation in many, many scenarios. Gas molecules, atoms, for instance, can be modelled as perfectly hard elastic spheres to a very high accuracy, like I was just describing. So ideal gases, collisions between atoms, they, to all intents and purposes, are elastic. So, as a plenary, can we define elastic and inelastic? It's to do with loss of kinetic energy. We remember in both of those types of collisions, linear momentum is conserved. In elastic ones, kinetic energy is also conserved. In inelastic collisions, some energy loss happens due usually to heat or sound.